Atomic Research, Kalpakkam, after serving there for 37 years. He has been mostly working on the nuclear reaction data for reactor physics applications and computer code developments related to this field. He did his BSc in Loyola College, Chennai, MSc in Annamalai University, and PhD in the University of Madras. His mentor was Dr. S. Ganeshan, ex-Rajaramana Fellow at BARC, still very active in the field. Dr. Gopalakrishnan guided one student for PhD. His PhD student, Dr. G. Pandin Kumar, is presently Scientific Officer in IGCAR, Kalpakkam. Dr. Gopalakrishnan has about 20 journal publications, over 60 reports, and 2 book chapters. He has taught basic neutron physics and reactor physics in IIT Kanpur, IIT Madras, and in the training schools of BRC, NFC, and IGCAR. He was on the expert teaching missions of the International Atomic Energy Agency IAEA on 2 occasions. He has also taken part in a few IAEA research projects also. He is with us in MCNS since 2014, sharing his knowledge. On behalf of all, I request Dr. Gopalakrishnan to deliver his talk on the topic nuclear energy in India. Why thorium? Welcome, sir.
Thanks, Dr. Kazu, and thanks, Dr. Sachin. With sincere pranams to Sir C.V. Raman, in whose memory this entire Science Week celebration is dedicated, I will go to the topic of my lecture. Nuclear energy in India and why thorium. This looks like a big S&T topic. Yes, it is, but still, in this small talk, I don't much go into the scientific or technical details. I try to make it, I try to tune it to the beginners, the uninformed kind of people, maybe school level or college level, who have no connection to this field. So people who are experts in nuclear physics or nuclear reactors may find it probably boring. And I think this kind of treatment will be quite useful for the mixed audience which I see here. And before going to the actual topic, so nuclear energy in India, okay, this is all right. Then there is a question here, why thorium? So for the nuclear energy, if I ask a question, why thorium, I expect a positive reply. Okay, thorium has this kind of advantages. Thorium is plenty, it is easy to use, it gives you a lot of energy. Okay, you give all these, then it's a good thing. So you have answered, the question is quenched. But if I, in addition to that, if I say that thorium has a lot of problems, okay, it gives energy, whatever it is, but it gives a lot of problems, then the same question will still remain. Why then thorium? Okay, if it is going to be problematic, why is thorium? Okay, so this question remains, and a talk of this sort should give some answers to this. I will not be definitely complete, but I will just try to throw some light on this, both the aspects. Both the aspects are true and they are present. I think I am making it clear. Okay, the theme of this Science Day, so we have extended the same theme for the whole week, given by Government of India, is integrated approach in science and technology for a sustainable future. Nuclear energy, so we are now dealing with the energy part of this whole thing, sustainable future or whatever it is. So if you are talking about nuclear energy, it goes without saying, it is definitely a science and technology area. Science and technology intense area is nuclear energy. And there are various sources of energy, and we need an integrated approach. So anyway, we'll see a little more also. So these two are okay. But the other thing is there, sustainable. How is it sustainable? This topic, am I talking about a sustainable proposition? Why is it sustainable? Then future. Okay, future, how the word future is relevant to this topic. In the case of thorium, it is a good fuel material for the future. It is a promising fuel material for the future. So that is one reason why it is future. The second reason is it is going to be a fuel only in the future. Okay, that means it is not a fuel material for the present. So it is future, and it has promises for the future. So in both the angles, this topic, thorium, is justifying the word future. So I think the topic which I have taken, nuclear energy in India, why thorium, is aptly matching the kind of theme that is given. Now, certain facts. Energy demand increases. Why at all we are talking about energy today as under this theme? Okay, energy demand increases. This is true for every country, true for India also. They have projected something like 6% energy growth, demand growth. Then these energies are met, this energy demand is met by generally, mostly by the so-called fossil fuels, which are the coal, petrol, etc. And then these are taken out from the ground and they get depleted and they become scarcer and scarcer. So some alternative is required. So support from nuclear source is promising to some extent. Okay. So then are we going to, if nuclear energy is there, are we proposing to throw away fossil? Okay, it is not that. We will live with it. We will support it. That's why I use the word support. So it is again an integrated approach. Do we have a plan? Yes, we have a plan. We are going to see it. Then this is, as I said earlier, this is a highly sophisticated science and technology problem. Okay, why? Why is it science and technology problem? It's not like taking some firewood and generating energy. It is S&T. And then are we capable? Okay, these are certain questions. And then what are the nuclear fuels we have? Uranium. Everyone knows in the world, even a school student knows uranium is a source of energy. And he also knows that it gives you the energy by fission. Okay, this uranium is the most prevalent nuclear fuel. Why? Why do we say it is most prevalent, but not sustainable with respect to India? It is only for short term. Why? Why is it for short term? Then when you come to thorium, it is not so prevalent like uranium. Why is it so? But it is sustainable long term. Why do we say it is sustainable and why is it long term? It is a future fuel. Why do we say it is a future fuel? And Indian nuclear energy program is set to depend on utilizing thorium. Why do we say that? I'll give some quick answers in case someone wants to quit early. So these quick answers are possible due to decades of hard work, collection of a lot of data, doing a lot of experiments. Okay. Then nuclear energy. So these are the points. The left side points were all there in the previous slide. Okay, wherever I have put Y, and these points only I am considering now to give you some answer. Nuclear energy, I said, is highly sophisticated S&T because it involves radioactivity, it involves remote handling, high energies are involved, and involves every department of science and technology. I don't think whether any other energy project will involve so many kinds of departments, science and technology department. And then that is one thing. Uranium, there were some questions also under uranium. The most prevalent nucleus. Why? It is ready to use natural composition. So you extract uranium and it is ready. And it is not sustainable. It's a short term. Why? Because availability in India is very limited. And in the case of thorium, not so prevalent, we said. It is not a ready fuel. Okay, why? We will understand that. And it needs man-made additions. Okay, and it is sustainable due to one count because it is abundant. In India is the 4th in the world with respect to thorium resources. And it is a future fuel. It requires a few decades of preparation. That's why it is a future fuel. It is not a ready fuel today. And crucial in indigenous nuclear energy program, I said. Why? Because it has proven potential, can sustain for a few centuries. And now, slowly we will understand why nuclear energy at all. Okay, why not coal and other things? What is the advantage nuclear energy has? There is a small comparison here. It compares uranium-235. It could be plutonium also. I have taken an example of uranium-235. More or less the same numbers hold for other fissioning materials. If you burn one atom of carbon, complete combustion, okay, you give the energy that is given. And then if you fission one atom of uranium-235, you can see the energy that is available, and ratio of fission energy to the combustion energy of carbon, see, it is 50 million. This is for one atom of carbon compared to one atom of uranium-235 fission. And just from this data, you derive the data for 1 gram. So the difference between U235 and this is 2.6 million. And 1 cc of these two gives 23.4 into 10 power 6. That is millions of times higher. Why did I give 1 cc also instead of, in addition to 1 gram? Because now you know that for a similar amount of energy, the size of a nuclear power plant compared to the coal power plant. Because just 1 cc gives you a million times more than that. If you want this much energy, a coal station has to be so much big. So that, and then nuclear power station is so compact. Then this is an additional information. 1 gram uranium fission gives nearly 24,000 units. The unit, by unit, I mean the kilowatt hour, which the unit for which we are paying money, 24,000 unit. 1 gram of uranium fission gives you 24,000 unit of energy. Okay, so that is why we are talking about the advantage is so high. Then in this context, so you can see also this curve. Okay, this curve, it says whichever there are a few candidate materials for use in fission, including thorium. Anything above actinium, thorium, uranium, all these isotopes of them, plutonium, and many other. All these things are fissionable in a reactor by proper arrangement, proper science and technology. But all of them differ only by about some plus or minus 5% in the energy production for fission. You can see this is only plus or minus. If you take this to be the midline, it will be varying between plus or minus 5. So anything is okay. And then comparison for thorium in India's resources, uranium is 40,000 tons availability. And thorium, which is 4th in the world, is 320,000 tons available. This is the old data. And I see some recent data. I don't know whether it is confirmed or not, but I'll give you that data also. It is much more than this. Anyway, these numbers are not very important. What we have to know is, compared to uranium, thorium is in very large number in India. Installed generation capacity in India. So we have to just see what is the amount of energy that each kind of fuel is given. So this is the very recent data, 31,122. Okay, so these are the things. Total fossil fuels, coal, lignite, gas, all those things, they give up to now 59.7% of India's energy is given by all these fossil fuels, and these I said are fast depleting. And then non-fuel like hydro. So these are all renewable sources. RES is a renewable source of energy, hydro, wind, and other things. So these are giving 30. It also includes to some extent solar, and 38.5% of the energy. and nuclear is giving at present very meager. It is only giving about 2%. And total non-fossil fuel is 40.3. Okay, so this is the distribution. Now this much of dependence is there on coal, so we can imagine how much we are going to deplete if we are going to depend only on that. So what is the demand? The demand is projected as 6%. Demand of electricity is projected as 6%. And now with all this known, how a government plans these energy source. The energy planning of a country or a state would involve the following salient considerations. Very obvious. The energy requirement along with the distribution of its purposes. Okay. The growth rate of energy demand. Available energy sources and their growth or depletion rates. The viability and costs of these sources. Then safety aspects, and very specific, very important for nuclear. Then other considerations like environmental aspects, public acceptability, and all that. These are also very important for nuclear specifically. Then various projections, scenarios and plans will be made for various periods in the near and long future, and this involves expert foresight and scientific, technological, economical, and social analysis. Okay, all these things combined together will decide on the kind of power sources. Okay, fission energy potential of the earth. How much when you are going to the nuclear, what is the fission energy that is available on earth? So in the form of uranium-235, see this is the mean concentration in the earth crust. This much of uranium and this much of plutonium is available, and what is the energy equivalent of that content? So that is what is given here. Now these numbers are not very important. The content of uranium-235 is 10 power 9. The content of uranium-238 is higher, 100 times higher, and the content of thorium is much higher. Remember, this content is per ton, not this. Okay, this is per ton, and here you see how much is available. This availability, thorium availability is more than 4 times the uranium availability. This is the India's, as I said, this is old data. Uranium is 40,000 tons and thorium is 320,000 tons. Okay, then this one, Atomic Minerals Directorate, AMD, under Department of Atomic Energy, they have given this data. So this is the new data I just mentioned a few minutes back. So this is the distribution of thorium reserves in India, and it totals up to about 12 million tons of thorium, and that promises about this is the monazite source. This is not the weight of thorium. This is the weight of the monazite ore, and it contains about 1 million tons of thorium. So that is this is the more recent data. So I mean, let us not much bother about. I may use this number also, because I have not seen a confirmation except the statement. But it doesn't matter. Thorium is in large quantity in India. That is what we want to know for this particular talk. Okay, now these pictures are just to give an understanding for the people who are unversed in this field, how the nuclear energy, say the nucleus is giving such a large amount of energy. Where is it stored and how is it given? Why is it giving at all energy? So this is the principle is hidden in what is known as binding energy. All physics people will know this. And see, this yellow area is called the nucleus, and within that there are protons, there are neutrons. These are collectively called nucleons. When they have to pack tightly, they have to release energy. Okay, there will be always a tendency to obtain the highest stability. That will be a natural stability, so natural phenomenon. So these nucleons would tend to go to the highest stability. To do that, in order to do that, they have to shed the available energy. If they have more energy, they will be free, so they won't be stable. If they have less energy, they have given away the energy, they are packed. And in case you want to separate them, you have to supply the energy back. Okay, that is it. This is called the binding energy principle. Okay, so this is 2 heavy hydrogen atoms I have given, and they combine to a helium. Okay, why do they do that at all? Why do they do that? When they are individually heavy hydrogen atoms, their binding energy is smaller than the binding energy of the helium. This is how this reaction takes place at all. Okay, so this similar concept is true for heavy, because I showed this example is for very light nucleides combining to form a heavy nucleus. This is called the fusion. And similar principle is true for heavy materials also. See, very heavy materials, when they are unstable, sometimes they split themselves into two for the same thing, for the same reason. See, these two smaller ones have much higher binding energies than the heavy one. Okay, so whichever is the way, either the splitting is the way or combining is the way, if the transition is going to take to a higher binding energy, average binding energy, then that will be favored by the nucleus. So going from a lower binding energy to higher binding energy means release of energy. That is why the release of energy takes place. Okay, when is this? The answer is given here in words here. When is nuclear energy released? When a transition or transformation to more stable configuration happens, there will be a release of energy. So this is how we are getting fusion energy. We are talking about fusion energy in earlier talks. They said the sun is giving you a lot of energy due to fusion, and this is the principle. And reactors are going to give you a lot of energy. This is the principle. That's all. Okay, and the same thing in the form of a graph. You don't have to bother about this one. This gives you an average binding energy in any nucleus. It is plotted versus the mass of the nucleus. Okay, as you see a very heavy nucleus here, so there is a decline in the binding energy, average binding energy. So this will have a tendency to break so that they come to the middle. So middle mass, instead of being so heavy, they want to become lighter so that they get higher binding energy per nucleon. That means they become more stable. Okay, and in this one, I just wanted to tell you importance of neutrons. Then very heavy nucleides, as I said earlier, I showed a picture that they can split to go to higher stable configurations. Okay, and fission, that is called fission. Splitting of a heavy nucleus is called fission, and fission can be spontaneous. In the next slide, we'll make it more understandable, more easy to understand. Okay, the fission can be spontaneous. For example, uranium-235 without any provocation can split into two and attain stabler states. Okay, like thorium, all these things can undergo spontaneous fission. This is called spontaneous fission. And then fission, this is in contrast to that, neutron-induced fission. Okay, you use a neutron, that what happens is same uranium-235, the probability of spontaneous fission is negligible, and the probability when a neutron hits it is tremendously increased, maybe 10 power 10, 10 power 12 times and all that. It's such a high probability. Okay, so in this one, the fissioning nucleus captures a neutron, and then the fission probability increases tremendously. Okay, so this is the point which we have to note. This is very important for me. Okay, it is not just for knowledge alone, and this is very important for me for my discussions. Okay, so that is why I have put important symbol here. The reactor power is due to the neutron-induced fission. So this one is not considered at all. This is unimportant, negligible for reactor power. Okay, the reactor power is due to neutron-induced fission in many materials. Okay, reactor operation is dictated by neutron population, because the neutrons dictate now. Neutrons are very important. So the reactor physics, the other name of reactor physics is neutronics. Okay, so the neutron population and the neutron availability, neutron energy, all those things. You talk about neutron when you are talking about a fission reactor. Okay. Then this is what I said. You can better understand it easily. It's a picture. So it is a fully blown in balloon. Okay. So if you blow a little more, maybe it'll break on its own. Okay. But somehow it stays now. Some resilience is there. But if you prick with a small pin, it is going to burst. So the neutron does this job here. Okay. So there are materials like beyond this thorium, plutonium, and all that, much beyond that. Like if you go to 260, mass equal to 260 and much beyond. So those nuclei do not, they don't stay. They are not available actually because they are not stable. The reason is they are more blown, so they burst. So such a nuclei you cannot even prepare. So these stable nuclei which are fortunately available, they are fully blown in, but they need some such pricking to cause a definite fission. So this is what is happening in a reactor. You have for every nucleus has to be pricked by a neutron. Okay, so now neutron is absorbed. So in the fission, as I said, the neutron is absorbed in a nucleus. Okay, fission occurs because we want fission. Our orientation will be towards fission. Fission occurs, and the fission produces one neutron causes fission, and the fission produces more than 2 neutrons. Okay, what a boon from the nature. You just think this particular line is so important for us, and this causes further fission because neutron is required for fission, and the fission is giving you more than 2 neutrons. So a chain reaction and power production becomes possible. Okay, you don't have to find a neutron for every fission. One neutron fission, then it gives you more than 1 neutron. So chain reaction in principle becomes possible. But so this is always whenever a neutron is absorbed, fission does not occur. It is a probability that it happens. So that is the next one. Neutron is absorbed, swallowed. It is swallowed by the nucleus, but no fission occurs. So this is another probability. Okay, that means neutron is absorbed and causes fission. Okay, it is we want it, and neutron is absorbed. That means neutron is lost. Okay, I said neutron population is important. If the neutron is lost, that's not a good thing. That's why I'm worried here. Okay, so this is the description of that fission reaction. So the neutron comes, hits the target, and it is absorbed, and then it fissions into 2 fragments, and more than 2 neutrons are produced. This is the fission, and this is the capture. In this case, neutron comes, hits it, it is absorbed, and it is not given out. Okay, if it has an excess energy, it just gives gamma and then settles down. So here, this is a neutron disappearance reaction or neutron loss reaction. This is a neutron production reaction. So we want it. Which one do we like? Because we want our reactor to work based on fission. So we want more probability of this happening in the reactor than this. How do we manage that? So in case this happens, so this is the chain reaction picture. A neutron comes, hits, fission takes place, 3 neutrons are produced. See, there is a neutron here, which is simply absorbed. There is another neutron, it causes further fission. So like this you see, some of them are absorbed, some of them are causing fission. This is what is really happening, and we have to strike a balance. How do we do that? Okay, now it depends on 2 things. Choice of a fuel. So this is the most, because I am talking about thorium, so this is choice of the fuel is the subject actually. So most basic consideration is this. First, look at the nuclear fuel. Nuclear fuel is meant to give continuous supply of fission energy. So our condition is fission probability should be greater than the capture probability. Okay, so this is what we have to see. This is the most important condition. Okay, now we have to see, because these are all God given. The data, the probabilities are not something which we can arrange. So you have to choose the material, and you have to know the properties of the material and what neutron does for each material. So for all these things you should do nuclear experiments and then obtain data. Okay, so from all those things, these facts are obtained. Okay, nuclear physics tells you this: fission or capture, take fission or take capture, it varies with the nuclide. That is, fission of thorium is different from fission of uranium, is fission of plutonium. So it varies drastically with the nuclide that you consider. And it also varies with the neutron energy, the energy with which the neutron comes and hits it. Okay, it is drastic variation in this and drastic variation in this also. But very high variation from one point to the other. Okay, you say 1 EV or 1.1 EV, the probability is very different. Say uranium-233 and uranium-234, the probabilities are very different. So such a drastic variation in this one. So all these are now available. Numerous experiments and theory calculations have been done, and a lot of data has been collected, and that's called the nuclear data. This itself is a subject by itself. Okay, so with assume that these facts are known, we have a table of the probabilities for against the nucleus at various energies and all that. Okay, this data is available. Now what to do with that? So this is the neutronics. What we are doing with this data is the neutronics to design a reactor. So study and choose, because our criterion is this: fission probability greater than capture probability. Now study and choose between these. Okay, the fuel composition, thorium, uranium, etc., fuel composition, and the neutron energy range that is favorable to you, which is going to give you fission by capture greater than 1. Okay, so this is the main principle. This is the easy principle. So this may not be so nice. This much explanation is somewhat crude. This is not okay for a reactor physicist, but this is okay for an understanding of the subject. Okay, but this anyway it does not contradict any reactor physics. Right? Then I am studying fission to capture ratio. So this is my purpose. Which energy region and which nucleus is going to give me fission by capture greater than 1. This is my study. So I consider materials one by one. I consider energy. So I can plot this from 0 energy to several MeVs. I don't want to do it here, and I'll just take only 2 regions, which are the practical regions for reactors. There is a slow neutron energy region and a fast neutron energy region. This is 100 kilo electron volts. So this is 0.025 eV. So don't bother about eV or kilo electron volt. This is a unit, but this is you just see the magnitude of this, relative magnitudes of these. If you take uranium-235, how does it behave? At slow neutrons, the fission to capture is 5.9, much over 1, and in the fast region it is again much over 1, 3.7. So uranium-235 is a good candidate. Okay, and then you take uranium-238 alone, and then it is neither in the slow range or in the fast range it is good. It is not a candidate. Uranium-238 itself cannot be a fissile, but cannot be a fuel candidate. Then you just make a combination of these two. Okay, then you take 0.7%. Why do you take 0.7%? There is a reason for that. 0.7% of U235 and the remaining U238. This combination is good in the slow energy region, but not in the fast region. Okay, then as you increase the fissile content, U235 content, it becomes better and better. Okay, so why did I put a star? Okay, it says this is the natural composition. When you extract uranium from the nature, it comes in this composition. Okay, this is a natural composition, and that is already fission by capture is greater than 1. So the natural uranium is ready as in the slow reactor, but not in the fast reactor. So it is a natural fuel. Okay, then go to another material. This is an artificial material. I have put it in red. It is not naturally available. It is a man-made material. Okay, man-made, though it is there, the properties are like this. This is also good at thermal or fast. In the fast region, this is even much better than that. And you can see the combination. So when you go to 20% combination, something like this, so this is very good in the thermal region as well as in the fast region. This is plutonium-239 in combination with uranium-238. Uranium-238, as I said, is useless on its own, but in combination, okay, it is accepted. Then uranium-233. This is another man-made material. Okay, so this is very good, much better than the other two in the slow region as well as in the fast region. By the numbers, I am saying this is much better than that. And thorium-232 alone, okay, it is much worse. It is the worst. Our candidate for the today's talk is useless in the thermal region, also useless in the fast region. And this is our hero today. Okay, so now you think of U233 and thorium-232 combination. As you increase the U233 presence in the fuel, slowly it improves, and in the when it is about 20% or so, it is very good in the thermal region as well as in the fast region. So these are all we have seen. Now these materials U235, Pu239 and U233, these are individually very good, as you see here, individually good candidates. So that is what this is, and they are called fissile. So the nucleides which are good which undergo fission in all the energy, any energy region. They are called fissile materials. This is just a nomenclature. So it is called fissile material. And U-238 and thorium-232 are individually not good, and at any energy. Okay, at any energy you choose, they are not good. Okay, so no reactor can work without a fissile material. Okay, reactor can have this, but without the combination of the fissile material, a reactor cannot work. This anyone has to understand this. And then this, as I said, is a natural composition, and uranium-235 is the only natural fissile. See, other things, as I showed you, they are all man-made. Uranium-235 occurs in nature, and that too only this much, 0.7%. But still, most of the reactors that we use, especially in India, most 22 reactors are there in India. Most of them use this combination. That means natural uranium. Okay. Then, based on fission to capture, these are the lessons that we have seen. No reactor without fissile. We said that. And 0.7% U-235 and 99, this natural uranium, fission by capture is greater than 1. So present day reactors, we have already said that. And thorium-232 is 100% in nature. It doesn't have a fissile component. Okay, so it is not good. Then why talk about it? Okay, so this question lingers with us. So then U-235 is okay, it is available. Plutonium-239 and U-233 are good at all energies we have said, but we said man-made. Which man is going to give it to me? Give them to me. Plutonium-239, U-233. Who will give? Okay, so the nature has to give. So that is this picture. You start with uranium-238, which is useless individually. Okay, in case it is there, why do we put it in the reactor at all? So in case it is there in the reactor and it captures a neutron, then by some radioactive procedure, it gives rise to plutonium-239. Okay, this was a waste and this is a wealth. Okay, so this is how, this is called conversion, or it's called breeding also. Okay, so the so-called useless material which is in abundance in the nature, from there you can get a precious fissile material. So this is similarly thorium-232, which also we said, why talk about it? We talk about it because of this. Thorium-232, if it is in the reactor, when it captures slow neutrons, it undergoes some radioactive processes and finally gives you U-233. So the useless thorium-232 gives you U-233, the useless uranium-238 gives you plutonium-239. So reactor, if it is properly designed and properly operated, it is going to give you new fissile material from those materials which are otherwise of no use. Okay, so it depends on design, it depends on choice, it depends on choice of the material as well as choice of the energy region. Okay, so how do we do that in an actual reactor? This is a reactor representation. This is called the core of a reactor, where you put the uranium-235, whatever fuel you have selected, you put here, and then it burns and gives you a lot of energy. You can send in a coolant, and coolant gets hotter, and you can take out the hot coolant here. Okay, this is how you produce energy. And how do we get the new materials out of this? Okay, so in this picture, this portion, the yellow-red portion, is the core region. So this is the core here, this is the core region here, and this is where I put fissile material, fertile material, and fissions take place, energy gets produced, fission energy gets produced. And surrounding that, we put our useless material, thorium-232 or uranium-238, big chunk of it, we will put surrounding that. Okay, so the neutrons that leak out, because every fission gives you more than one neutron. Okay, the fission chain can sustain with one neutron. There are excess neutrons are there. They are fast. They will leak out of this boundary, and then they will enter this region, and they will be captured by the fertile material, captured by the uranium-238 or thorium-232, which you put here, and then as you have seen in the previous slide, fissile material will get produced here. I will show once again. So either this or this you can put in the green region, and you will produce the fissile materials there. So this is the fertile material. Why is it called fertile material? Because this is useless material, but it gives rise to a useful material. So it is fertile. So fertile becomes fissile in this region. So U-238 becomes plutonium-239 and thorium-232 becomes uranium-233. And you can estimate how much is produced because you are consuming you are consuming fissile material here and you are producing fissile material here. You can have the ratio, how much you produce to how much you burnt. So that is called conversion ratio, fissile produced to fissile consumed. And I mean, it is something wonderful. You can produce more fissile than you consume here in a reactor. You go on putting fuel here, and at the end of a period, you will see you have produced more fissile material than what you consume here. So it is like giving interest for your investment. It is something like that. So that is conversion ratio greater than 1 is called breeding ratio. Okay. So the reactor concept where this kind of breeding takes place, that is, you produce more fissile than you consume, such reactors called breeder reactors. You have thermal breeder reactors, you have fast breeder reactors. That's why we say FBR and things like that. Okay. So then now some more questions, and some of them repeated also. Why thorium? The question remains, and India is enriched in thorium. So okay, happy. Then thorium reactor. Think of a thorium reactor. But natural thorium lacks a fissile material. Okay, not good. What to do? Nevertheless, thorium is good breeder material. Okay, again happy. Okay, it produces uranium-233. Okay, now you think of thorium uranium-233 reactor. But then this is okay. But this uranium-233 has to be produced. Initially, you have to give uranium-233 to this reactor. So it has to be produced in other reactors. Okay, several reactors have to run for several years to get you enough uranium-233 to start a thorium uranium-233 reactor. Okay, adequate amount you have to prepare. So in a thermal reactor, 3 to 4% must be U233. In a fast reactor, it has to be greater than 20%. Okay, then how much is adequate? It will be in tons. You are saying 3-4%, but it will be in tons. Okay, so also this is another problem to keep your face like this. Uranium-233 shows unique radiation problems for handling. Okay, why still thorium? So the question has come again. So do SNT because it is abundant, it is promising. Do a lot of SNT to tap the available because you have it. You have only that. And then this is the that unique problem I said. So this one U233 shows unique radiation problem, and this is the problem. So uranium-233 in a reaction called N2N reaction, it undergoes certain radioactive processes, and it produces this material called tellurium-208, and it emits a gamma ray of very high energy. This is called hot gamma. It is very difficult. If this is there somewhere, if U232 is around you and you cannot go near it, okay, it requires a large shielding and remote handling, automation, and all those things. So because of this hot gamma, okay, then and how much of it is happening? This is dangerous. Then you can leave out, isn't it? I don't want uranium-233 because of this problem. But how much of it happens? See, a small fraction of the fissile product undergoes this reaction. See, in a thermal reactor, so most of the neutrons will be, as I showed you, below 1 eV. eV is a unit of energy, 1 eV. But for this reaction to take place, okay, it requires 6 million eV. Okay, so most of the neutrons are around 1 eV only, and if you go to 10 eV, it reduces by factors. Okay, but when it goes to a million eV, then practically there won't be neutrons. So there will be 10 orders of magnitude reduction, but still some neutrons are there, and they are captured, and a small amount of this is produced. Okay, so a large amount of advantage is okay. You can even ignore it, but a small amount of problem you cannot ignore it when you want to handle, and that is this. Okay, so now with all that we have given, now we are thinking whether to have thorium reactor or not thorium reactor. So these are the considerations. So what is the energy potential of different fuels? So coal is 100. So what is given here is the amount that is available in billion tons or something, whatever it is, and then here coal equivalent in billion tons is given. So for example, when you say 0.6 billion tons, it is equal to 1.2 billion tons of coal. Okay, energy wise, 0.6 billion tons of oil is equivalent to 1.2 billion tons of coal, like this. Now you come here, 40,000 tons of uranium is equivalent to 0.8 billion tons of coal. And if you use it in a thermal reactor, so-called PHWR reactor, and if you use it in a fast reactor mode, it is much larger. 40,000 tons of uranium is 130 billion tons of coal. And with respect to thorium, thorium means we have in mind thorium uranium-233 reactor. It is available 320,000 tons, and if you are using a thermal breeder concept, then it is equal to 360 billion tons of coal, and this is 1,000 billion tons of coal. So this is the advantage. This is how we have to linger on to thorium, even though there is problem. You develop your SNT so that you are able to tap. I have to finish fast. Then advantage thorium. Then it has natural fissile, advantage uranium. It has natural fissile, and uranium-238 breeds plutonium-239. Both are good. Advantage. Okay. Disadvantage is scarcity. Okay. You have to import, and import is very expensive. And in addition, this I didn't mention, minor actinide production. There are minor actinides are some heavy materials which are above uranium-238 in mass, and they give radioactivity problem, and they are long lived. It is difficult to burn them. They are also produced. See, 1 ton of uranium gives you only 600 grams of these minor actinides, but still they are radioactive, so hence you have to be careful. So none of these disadvantages that I am showing is going to advise you to throw away. It is only telling you develop your SNT and manage it, because safety is number 1 point here. And then advantage thorium. It is plenty. This is the main advantage. And thorium-238 also breeds uranium-233. Okay. And thorium-233, this breeding, uranium-233 breeding, that is breeding means it gives more fissile than consumed, and that can happen in thermal reactor as well as in fast reactor. So that is the additional advantage of uranium-233. Minor actinide problem. This problem is absent. So these are all advantages of thorium. So okay. Then disadvantage of thorium. So as we have said, it has no fissile component. So you have to artificially add it. And the decay problem, as I said earlier, uranium-232 decay product. And so this needs thick shields and all that. So, but this is what we have to remember. Solutions available. If you are doing good SNT, solutions will always be available. Solutions are known to be available. There is a Kamini reactor in IGCAR. It's a small reactor. It is used for experiments. It uses uranium-233. Okay, it is not for power production. It is for experiments. Okay, so anyway, a uranium-233 reactor, a model kind of reactor, is working already. That means we have the know-how of extracting uranium-233 from the thorium-232 fuel, and we are able to use it in a reactor. Know-how is available. It has to be done in a large scale when it is produced. Okay, this gives you hope. And then see, based on all this, okay, India has charted out a 3-stage program. So Dr. P.R. Vasudev Rao in his talk mentioned about the 3-stage program. This is due to Dr. Homi Bhabha. Homi Bhabha drew this plan, and it still is there, and India talks about this. Okay, what are the 3 stages? So stage 1, it is already running. We have got 22 reactors working, and each one is giving a minimum of 200 megawatt, and some of them are the capacity is higher. So, and what should we do in the first stage? We have these reactors. So run several natural uranium reactors, okay, and accumulate plutonium. U238 will give you plutonium and accumulate a lot of it. And that is, why do you accumulate? For use in fast reactors. Why do you want fast reactors? So fast reactors breeding ratio is greater than 1. Okay, that is the reason. So then the second stage is, with the accumulated plutonium, you go to fast reactor concept. Okay, then stage 2 is fast reactors. Run several fast breeder reactors once you are ready, and with plutonium that is produced here. And in this, when it is successfully running, then you also put some thorium in the blanket, and you produce uranium-233 here. Okay, so that will be fed in the 3rd stage. So this is how. So now between this stage and this stage, several decades have to pass, because it requires several reactor years. And between this stage and this stage, again, several reactors have to pass. And this thing, we have set foot on this one, the 2nd stage. We are successful in the first one. We have set foot on this. That's why we have a PFBR, prototype fast breeder reactor. It has been constructed even when I was there. It has not started, so it may start anytime. Okay. Then if these two are successful, we are ready to go to the stage 3. Stage 3 will be using our hero, who is thorium-232, because by the time we will have enough uranium-233. If we have accumulated, I said tons are needed. If they are available, we will start. Okay, we can either use thermal breeder technology or fast breeder technology, and once you are successful in this, go on. Okay, this reactor is going to, this combination is going to work for centuries, several centuries. Okay, this is the promise. I was mentioning the word promise. It promises this kind of a scenario. Okay, here the breeding ratio is greater than 1 here, and breeding ratio is greater than 1 also for fast reactors. Once the breeding, you are going to produce more fissile than you consume, then what is the problem? So it is going to give you, it will go on giving you U233, and you can exhaust thorium-232. And thorium-232 availability in India is very large, so it will cater to your energy needs for several centuries. Okay, but still we are now about 2% in energy from nuclear, and our plan itself is not to reach 100%. It is impossible. So it is an integrated approach. All these things will be there, and this component will go up. I mean, the ambition is to go up to 20%. Okay, in a few decades from now, 20% only. Okay, so we are now 2%. We have to multiply it by 10. So that is the situation. And as I mean, this one, the small one, decades, this is going to tell you what kind of delay it is going to be to go to this. That's why I said it is future. It is future. Okay, we are going to see this. Then, when are we going to the stage 3? If your talk is on thorium, we must be in the stage 3. Stage 1 and stage 2 don't have thorium. It is only irradiation. It is not a fuel here. It is a fuel here. Thorium is a fuel here. And when are we going to go there? Okay, this is the question. And this answer, because instead of my telling, I am quoting from AEC chairman, Dr. Anil Kakotkar. He has mentioned in one of the interviews, and he is talking about the 3 stages, and he says this. However, this is about the 3rd stage. The time frame in which thorium can be deployed has to be carefully selected. Okay, introducing thorium in the 1st stage or early in the 2nd stage of the program will adversely affect the rate of growth of nuclear power generation capacity, because we have to produce power. Our reactors are not for producing uranium-233. Reactors are for producing power. But if you are using these reactors for producing uranium-233, you are going to put thorium there, and the power production in that reactor will come down. So when you give substantial stability to the reactors, then you can produce this. Okay, so that is how. So the large-scale deployment of thorium is therefore expected to be about 3 to 4 decades. 3 to 4 decades, not from now. Okay, 3 to 4 decades after the commercial operation of fast breeder reactors with short doubling times, when thorium can be introduced to generate uranium-233. So this much we have to wait. Stage 2 must be mature and stabilized. Then the PFBR is yet to commence. That is the stage 2. Okay, so it has to commence. Many 2nd stage, many commercial reactors have to come. Lot of U233 has to be produced. Then only it will start. So it will be several decades from now. It is probably not for the youngsters who are sitting there. Okay, they will be doing a lot of SNT and make thorium to U233 reactors for the future. Okay, so this is summary. Thorium is the only indigenous answer to nuclear energy demand in India. Then it has potential and is promising, but not a ready fuel. Also problems exist and solutions exist too. But decisive, committed, planned efforts are needed. But it is worth it because it is our own resource. Thorium has a right and duty to help us. Let us oblige. Thorium wants to help us because it shows promise. Let us oblige thorium. Okay. The following are 2 out of 1,332 liners Sage Thiruvalluvar has given in Tamil some 2,000 years ago. These are very apt to recall at this point. The first one is Gunanadi Kutramum Nadi Avatrul Miganadi Mikkakolal. So it says, study the merits. When you are venturing on something, study the merits and the demerits. select without much problem, select it if the merits excel. Okay, so no confusion here. It's a management advice. Then the other one is also more apt because thorium shows a lot of problems also. Tunbam vaattu inbam payakkum vinai. It says venture into any activity capable of giving lasting happiness, even if it involves hardships to start with. So don't worry because it gives problem. If it has a potential to give lasting happiness, then you must enter it. So these are the two things that are required for addressing thorium as a fuel in India. So I have finished my lecture, but I just go. So it is not possible to read. These are these are some reactors that are operating in India presently. These are all thermal reactors. Okay, so the power that each one is producing is given here. Okay, and these are the different places where it is the names of the reactors. Okay, and these are working reactors as of now, and these are the planned reactors. So many reactors are also going to come. The date of construction start is given, not date of commissioning. These are the dates when they are going to commission. Some of them must have started. So Kakrapar, etc. Okay. Thank you very much.
Yeah, thank you very much for the very nice lecture. I particularly like you started the lecture with a lot of whys. Yeah, this is the asking why is the essence of science. So it's very, very suitable for this occasion of celebration of Science Week. So now the time.
I also gave answers to them.
Yeah, okay. Yeah, I also wanted to mention that you gave a very nice answers to the what was twice. Yeah, so the time is open for questions.
So it was an excellent, wonderful talk for all sections of audience, from beginners to even experts. And I liked your thank you because it has both uranium and thorium. Okay. So my question is regarding the thallium-208 production. Are the problems solved, or because in handling of uranium-230 thallium production, is the problem solved because 3 MeV gamma rays will come?
I can't say problems are solved fully because I do not know the status. But that is why I showed you for some promise, Kamini reactor. Uranium-233 has been taken, it has been handled, but large scale handling of thorium, uranium, for example, uranium produced will have this problem. But I think people are capable and the technology will come. And I don't think it is an unsolved problem forever.
Okay. And the other question is regarding the waste, radioactive waste. Right now, that is basically putting a brake on the fission and fusion energy.
Okay.
Because the radioactive waste goes through millions of years. Because no civilization lasts more than 100 years, 1,000 years. Yes. In history, no kingdom lasted more than 300, 400 years.
Yeah,
this is
but
why not transmutation being taken up? Instead of
storing that has to be done.
The entire globe is covered with all the fissile media, radioactive waste.
Correct. Most of the points against nuclear installations is this waste management only. So, but so far nowhere in the world waste is thrown away anywhere. Waste is not in any public domain. Waste is kept there itself. There are various procedures evolved for managing the wastes. Okay, so that it has to be very carefully handled, but there are procedures. Another thing is they have to be kept, okay, sealed and kept for many thousand years. This is the problem. It is easy, you can store it somewhere, but they have to be stored. Not during your lifetime, it has to be stored for many thousand years. So that is a concern. Okay, but that has to be done. And see, all these materials, uranium or thorium, all those things were there under the earth. They were all radioactive. You have taken out from them, and a little more problem you have added there. Okay, but whether you want or not, radioactive materials are there in the earth, and thorium monocytes are all there in Kerala, Tamil Nadu, everywhere, and they are radioactive. The problem is less. because man, whichever, if a natural resource, a natural thing, if man enters there, there is going to be a problem, and man has to solve that problem. Okay, there are a lot of things. You can go by bullock cart, but we want to go by flight. A single problem, 230 people, 300 people, even 700 people can die. So this kind of things are there possible. So you have to work out. So as of now, the probabilities, risk probabilities of nuclear waste has been considered to be very, very small, except for the radioactive waste problem. If it is in principle accepted, they can be stored. There are procedures available. If objections are there, then objections have to be answered. So there's a lot of responsibilities there on the S&T people who want to promote nuclear energy.
I want to share with you, somewhere I read one information. The fission technology problems and the fusion technology problems, the science and technology problems needs 20 million man years. Means 1 million students are required for 20, each student is required for 20 years to solve the problems.
No, I don't think, I mean, we may not gain much by answering such questions. They are theoretical questions. We are seeing a lot of effort is going on even on fusion. So something is happening now. I mean, it is going in the positive direction. So answers are coming. And lot of fission reactors, the world over 450 fission reactors are working. India itself, 22 reactors are already working successfully. And we are masters in thermal reactor. We can build, though we have bought Kudankulam, this is for a different reason. India can, if India proposes to build a PHWR now, if the fuel is assured, then they can successfully start the operation in the next 5 years. We have mastered the technology of heavy water, and we have generated a lot of energy through PHWRs. So successes will come if sustained efforts are made.
Thank you for the nice lecture and the creative slides, sir. My question is regarding the timeline you mentioned. You mentioned that about a decade time scale will be taken from one stage to another stage.
Not about a decade, several decades.
Several decades,
yes.
Yeah. So considering the new planned construction of the reactors, how much this construction will affect or shorten the length, this time scale?
After you start digging the first pour, they used to say, dig and first pour of the concrete at the bottom, then above which the reactor is going to this one. It will take, for a reactor concept where you are a master, like as I said, thermal reactor, it takes about 5 years. And for a reactor for which you need a lot of input, lot of interaction, all those things, you also study while you do the construction, then it may take 10 years. Okay. And so in about 10-15 years it took for the PFBR to be constructed in Kalpakkam. It was constructed, ready, even now, even 10 years back it was almost ready, the vessel was inserted there. But due to some policy decisions, still it has not started. That's a policy decision. I don't think it is a technical reason.
No, sir. Considering the timeline you mentioned, about 30 to 40 years for one stage to next stage completion, considering that all the planned reactors are done in a proper time scale, how much this time scale will be reduced?
Okay, reduced?
Considering that this reactors
actually,
will also...
No, there is no reduction. So in that I mentioned some decades, some 2-3 decades from one stage to the other. So now we are ready with the first stage. We can start anytime the second stage. Second stage has to work for 3 or 4 decades so that it accumulates enough uranium-233 to enter into the third stage. So this will be easily 3, 4 or 5 decades because you need so many reactor years to produce a few tons of uranium-233 accumulated and protected. And then you can start. So from now you can think it is easily 40 years or 50 years. That is why I said the youngsters will do S&T for uranium-233 reactor and give to the future people.
Thank you, sir.
Did I answer your question? Thank you.
Thank you, sir, for the very nice presentation. It was very simple. Like you have explained it in a very simplest way to the extent that a non-physicist can understand it easily. So I have a similar question like what Sweda asked. In one of the slides, you have mentioned that whether it is possible to precede this process instead of waiting it for 30-40 years by just focusing on what is required, because anyways it is going to contribute only 2% of the needs. Why can't we stop it and start focusing on what is required, so that this 2% can be compensated in any other, for example, any other renewable resources? Because in one of the slides you have mentioned that it will adversely affect the rate of growth of nuclear power generation capacity as of now.
Correct.
So only 2% is being supplied from this as of today. So why can't we proceed this process instead of waiting for 30-40 years? So because the output is going to be 20%, as you said, once it is done.
I don't know which output is 20%.
No, you are trying to reach it to 20% to meet the demand.
Total.
So for now it is only 2%.
Yes.
Instead of waiting for 2 or 3 decades, what if we halt it all together? Yes. Where the 2% item it is contributing can be compensated from any other resources.
What you are in effect saying is, put thorium not in a reactor, put it elsewhere, and go on producing U23. Okay, you need.
Expecting the answer, not the thorium. Forget about the nuclear power itself. Other renewables.
That's what I'm saying. Not in reactor, put it elsewhere. So you just another production of U233, some other thing, but you need neutrons. Okay. There is also another which I didn't mention. There is one thing called ADSS, okay, which what is that? Accelerator driven subcritical system. This is one thing where it gives, I mean, where you are seeing 2-3 neutrons produced per fission. There, per interaction, it gives you 20 neutrons. Something like that is possible. So there you can produce this one, but that requires a proton accelerator. There are problems. So the best and the easiest way is to use the reactor neutrons. Okay, you have to wait for it. Okay, other things are also not easy. There are other procedures which are not easy, which are more difficult than this, and it involves a lot of money. Okay, that's why that is why the 3 stages are given, carefully thought of 3 stages.
Thank you.
It is expected that next in 100 to 130 years, coal will not be available.
Yeah.
Petroleum products will not be available.
Correct.
The fossil fuel will be completely depleted. It is
Correct.
costlier to extract them.
Yes, and also coal, it has other uses. So we will lose. So everything we have to import.
Apart from India, is there any other country which is using thorium as a source?
No thorium reactor so far, anywhere. So in many of the other countries like USA or Russia, they have a lot of uranium left, and their hydro is very nice. So France is a place where enough fossil is not there. Hydro also is not good. It's all stagnated, and they are using something like 70% of their total energy is from nuclear.
Okay. So I mean, in terms of total energy budget, which country has the topmost country which is using the nuclear power as a source of?
If you see that way, it is United States, the highest. But percentage of energy wise, it is France within their country. But the amount of energy that is produced, if you just see the installed capacity, USA stands on the top.
Use these reactors. They are huge reactors meant for producing energy, like energy in the sense mostly electricity. Can we use smaller versions in automobiles so that we don't have to, nowadays we are moving into battery, instead we straight away move to
correct
nuclear.
In principle it is possible. In principle you can construct a small reactor and then put it in an automobile, but there is a driver sitting there, so you have the radiation problem. So if it is not there, so if it is going to be an automatic automobile, then it is okay. So submarines, spaceships and all these things use even now, and people who are operating there should be, see, near reactor people are going, they are operating. Like this, the people who are trained, who are capable of also handling that can be there, and such things are there. Submarines, submarine version is there, and the space version also is there. Space, because nobody is there in the spacecraft, and it can have a reactor, but the fuel is very different. So what they need is a lot of heat, and there are other fuel, more dangerous fuel, which gives a lot of heat. Such things are used in space ships. So it's possible. In principle, it is possible. You can have a small reactor and you have to accommodate it. Just like you put a cylinder in your car. So like this, you have to put a cylinder, which is a reactor. And then in principle, it is possible. But associated problems are there, waste fuel management and all that, where will you do? So that's the main question there. So such problems you have to address. So it will not be, see, we are constructing a reactor in a remote corner. For that itself, there is such a public, opposition. And if every car is going to have a nuclear reactor, nobody is going to accept it. That's kind of problem. Science, and as long as S&T is concerned, it is possible.
Thank you, sir, for a very simple presentation.
Thanks.
And in the end, you were mentioning about heavy water technology. So what is the role of heavy water?
Okay. So I was telling you, can I have some few minutes to answer this question? Okay, because it's already time. Okay, so there are, I was talking about a thermal reactor, the slow neutron reactor. When the neutrons are produced in fission, as I said, when the neutrons are produced, they have an energy of 2 million electron volts. Okay, but we are talking about a slow neutron reactor. Okay, that means the fast neutrons have to be brought down to the slow region. Why do we need the slow region? That is the region where the fuel behaves as we want. Okay, so the fast neutrons have to be brought down to such a low energy region. And this is done by introducing light water or heavy water in a reactor. Okay, heavy water has 1 proton more in its nucleus. That's all. It is doubly heavy. That's all. So otherwise there is not much different. It is also water. So in natural water, for every 65,000 liters of natural water, 1 liter of water is heavy. Okay, that's how it is. Why is the heavy water there? So the neutrons that are produced, when they interact with the heavy water or light water molecule, atoms, then they will interact with the hydrogen of that, the heavy hydrogen of that. And then when a particle is hitting a particle of almost equal mass, it has a high probability of reducing its energy. Like that by repeated collision with hydrogen or heavy hydrogen, the neutron loses an energy very fast. Okay, in about 20 collisions. Okay, 20 collisions from a 2 million electron volt neutron, in about 20 collisions with light water, it will come down to this energy. Okay, imagine uranium-235. If it is going to hit uranium-235 so many times, it requires something like 2,500 collisions to come to this stage. So that is why light materials are put in this only in order to reduce the neutron energy. There the difference is between light hydrogen and heavy hydrogen. Okay, light hydrogen has only 1 proton, so it has an affinity for one neutron, so it can take. Okay, so it absorbs a little more, whereas heavy hydrogen is already saturated with a neutron. It has no affinity for neutron, it doesn't absorb. So it manages the neutron population. As I said, a light water absorbs more neutrons than a heavy water. So in effect, a heavy hydrogen or a heavy water is a better slowing down agent. We call it a moderator.
Thank you, sir.
Thank you.
Can I ask one last question? So whether it is cost effective, what is the average amount that we are spending for each unit of energy that is produced through this process?
Actually,
and whether it is comparable with the other process like renewable resources?
Nuclear energy is not very costly, but it may be costlier than your hydro. It is cost, maybe suppose you say it is 1 rupee per this one unit hydro. This may be 5 rupees, something like that. But they are managing that somehow. So there is the policy of charging. It is not very expensive, and if a large number of reactors are there, it will even come down. But if you take solar, as of now, 1 rupee, this one will be 25 rupees now, 1 unit, if you solar as on date. Okay, but I said it will take several I mean, the thorium reactor will continue for a few centuries, maybe 200, 300, 400 years it will come. So the hope is by that time it gives you some amount of energy. By that time your technology will improve and you will set foot on other kinds of energies like solar. Solar is also promising, and you will find best methods for using solar everywhere. Okay. So once you set foot on solar, once you are stabilized on solar, nothing more is required. But there is much future. If I have to put 2 U's here, I have to put 5 U's for solar. Future it is.
Is there any question?
Yes, here.
Okay.
I have one question regarding this one. Since like uranium-233 is also undergoes fission due to neutron collision.
Uranium-235.
33. When it is produced, when it becomes fertile, so it also undergoes fission through neutron only. So how do you protect when it is when you are you are putting a thorium and surrounding it around the fuel? How do you protect uranium-233 not to undergo fission with the neutron already present in the reactor?
No, we don't protect. So they are in the so-called blanket. They are produced, and they are also produced in the core, because core contains thorium-232 or uranium-238. There also fissile is produced. A part of them take place in further fission. Some of them are depleted there itself. So after a given period, you have to look at the reactor, close the reactor, take out these materials like this, and put fresh fuel. It is a question of management. Okay. So many of them will be converted because large amount of neutrons are there, and many of them will be converted to fissile, and some of the converted fissile, produced fissile, will undergo fission. They will be lost. But what remains is your gain. Okay. And that gain can be more than what is consumed.
So even after that?
Even after that.
More
so
than
after a period, you fix a period like 6 months. Okay, 6 months you put the fuel, and then now you put the fissile in the core and fertile in the blanket. Okay, after 6 months you take out and find out how many U233 are there, how many of U233 that is consumed. Okay, so in a breeder reactor, what is produced is more than what is consumed.
Including the fuel which we have used.
That's called breeding gain. That's why I said it is interest on your investment. And this interest, if it is properly managed, it can be compound interest.
Sir, I have a simple technical question. We are going to the stage 1 to stage 2, then to stage 3. My question is whether the radioactivity waste that is produced per 100, let us say per 100 megawatt of energy, whether it is lesser in the later stages or it is more, or it is comparable, how it is?
So it is difficult for me to say. It is not my field, but it may not be less. It may not be less. It may not be greater. If you fix now the amount of radioactivity waste per unit of energy, then more or less it will remain the same.
Okay, so thank you.
Because problems are there, even U238 also, because minor actinides are there. And in the U233 minor actinides are not there, but U232 is there. And the design of the U233 reactor is different from the design of the other reactors. We are talking about molten salt reactor and all that. The concept is different, where the fuel itself will be running. The other reactors, coolant is running, but in the molten salt reactor, the fuel is in the molten stage, and fuel will be running. When it comes into the reactor, it burns and then comes out and circulates. While it is done, on the way, the fuel let out will be removed. So the technology will take care such that U233 is removed with much less production of U232, and still it will be produced and it is dangerous. So technology has to take care. Automation, remote shielding, all those things. Already even in the normal reactors, there is a lot of things which are done automatically. Humans cannot touch many things, everything, even experiments. So which are all done. The chemistry labs and all that I have seen. What is that called? Remote handling.
Remote handling terms.
So all these things are done. So even you take a test tube and put a little solution in a test tube, it is done by a machine. So that kind of thing. So
yeah, so I think now time is up. We don't have enough time.
yes.
Yeah, so very nice lecture and invited very.
Thank you.
I think no time really. No question. Yeah, so I believe yeah, Professor Gopalakrishnan can have answer questions upon questions sent by email. So
Sure.
or after
Sure.
Yeah, so we
I can
close.
answer if I know the answer.
Yeah, so we close this session for now, and yeah, so let's thank the Professor Gopalakrishnan again.
Thanks.
And
Thanks,
next,
Dr. Kasu. Thanks,
next-
Dr. Srijit, for giving me this time slot.
Thanks.
Thanks, everyone.
Yeah, so next session will start from 5 p.m. Yeah, so please come back.